So when we look at solving these equations using CFD, we have to look at our discretization. We look at this idea of the finite difference method. So we start with this equation, which is a differential equation that we're trying to solve with a particular initial condition or boundary condition where at x equals 0, u must be equal to 1. And we want to solve it at these 4 points, at 0, 1/3, 2/3, and 1. So we use Taylor series expansion to approximate the derivative using the current value and the previous value. Now, there are additional terms in the Taylor series expansion based on delta x squared and so on and so forth. What we're going to do is ignore those terms, and we say that this is second order accurate because we're neglecting terms with power greater than 2. So if we substitute this into our first equation, we come up with a new equation that relates the u at the current position I with the u at the previous position I minus 1. And then we can create this matrix of values. So we have an equation where u1, or u at x equals 0, has to be 1. So 1 times u1, 0 times u2, 0 times u3, and 0 times u4 all adds up to 1, which tells us that u1 equals 1. And then we have another equation for u2, and an equation for u3, and an equation for u4. So this matrix equation represents 4 individual linear equations. So this finite difference method is very good for structured meshes, but it does not handle unstructured meshes very well. When we have unstructured meshes, it's usually better to use what we call the finite element method. Finite element uses the method of weighted residuals to approximate the equations with a curve fit. It is much more complex than the finite difference approach, but it can very easily handle unstructured meshes. So a lot of CFD codes make use of it. We also have the finite volume method. The finite volume method puts a control volume in each cell, and it uses the control volume conservation equations on each cell, and then it approximates the gradients on the surfaces with the Taylor approximation. What's convenient about this is it guarantees convergent conservation, so mass must be conserved in the finite volume method. However, it does require us to calculate gradients at cell faces, and that just because conservation is guaranteed, it does not mean the results are going to be accurate. That's going to depend on your equations and your solution algorithm and so on and so forth. So once we've written the equations as a matrix, we can solve in 2 methods. We can solve directly, or we can solve by iteration. So direct solutions require a lot of RAM. They're a very large storage requirement. And it also has some other requirements. The matrix has to be singular, it has to be invertible, and there's some other conditions. So we can actually look at our matrix from the previous case, and if we use a row reduction, we can solve this matrix to look something like this. Now this is an easy matrix to solve by row reduction, but when you have a large matrix with thousands or millions of elements, of equations, these can be a little bit unwieldy to solve. We can also use iterative methods, and these are much more widely used because they're more computationally efficient, but they're not always as accurate. So we have this guess and correct kind of idea where we have an initial guess, and then each step we progressively improve our guess until we have a good result. One of the simplest examples is the Gauss-Seidel method. So we start out by taking our equations and we make a guess of 1, 0.75, 0.5, and 0.25 as the values for u1, u2, u3, and u4. And then we take these values and we run them through the equations to calculate new values. And so our second step, we get slightly different values. Then we do it one more time for our third step, and the values update a little bit more. And then finally, our fourth step, the values haven't changed very much, and we call this a converged solution. We'll discuss this a little bit in more detail during our heat transfer course next semester. But what's important to note is that the solutions that you get from these methods don't exactly match the real case. Now, for 4 nodes, which is what we did on the previous slide, you can see here we have this blue line, and there's some difference between the numerical solution that we calculated and the exact solution. Now, we can reduce that difference from our direct solution by adding nodes. And when you get up to 16 nodes, we see that there's almost no difference anymore between the exact solution and the numerical solution. So we have a better quality solution. If we look at iterative methods, here you can see we have this exact solution for n equals 4 nodes, and after one iteration, these two cells aren't so bad, but this last cell is still not very good. So after 2 or 3 iterations, we start to see the values match, and they get very close to what you see over here for the exact solution, or the direct solution for 4 nodes. Now, we have a few things we need to talk about when it comes to numerical methods. The first is accuracy. Accuracy is the actual correctness of the numerical solution when you compare it to the exact solution. So that's what we were looking at on the previous slide. It's comparison to the exact solution. Now, it's often difficult to really understand the accuracy without a lot of experimental data. So we use the truncation error as kind of a substitute. It gives us the effect of truncating the Taylor series expansion. Basically, the truncation error tells us how fast error will decrease as we decrease the mesh size. But it doesn't tell us the actual error of our current mesh. It just tells us how fast error will increase or decrease as we change the mesh. Consistency is talks about the derivation of the equation. A consistent method is one where the truncation error becomes 0 as the mesh size becomes 0. So what that means is that your discrete equation actually approaches the real equation as the step size becomes 0. So it means our discrete equations become the actual equations in the limit as delta x equals 0. Now, not all equations that we use in CFD have this property, because sometimes the algorithm used to solve the equation actually adds additional terms to help make the solution more stable. So consistency is an important parameter to remember. Stability is also a big issue. It's a property of your solution method and the basic equations. And what it means for a solution to be stable is that errors tend to damp out over time rather than be amplified. Unstable solutions will not converge to a result. They're what we call this divergent solution. Now, instability is not always bad. Some equations are inherently unstable. In fact, the Navier-Stokes equations are inherently unstable for high Reynolds numbers. So an unstable solution to the Navier-Stokes equation doesn't necessarily mean that there's an error in your algorithm or your equations. It may just be a feature of the system you're trying to predict. So it's important to understand how the system is supposed to behave so you can evaluate the quality of your numerical results. We also need to look at convergence, which is whether the solution can actually obtain a solution. Whether your algorithm can actually come up with something that has meaning. Just because a CFD solution converges does not mean that it's accurate. We have to look at accuracy, consistency, and stability as well. So just because you get a solution doesn't mean it's the right solution. Now, we're going to just very quickly look at an example that a graduate student here did to look at the Missouri S&T research reactor and look at the flow between two of the heated plates. So we start out with the reactor, MSTR, and then we go back down and we look at the individual fuel assemblies, and we break the fuel assembly down into the individual parallel plate fuel elements. And we take one flow channel that exists in between two plates. And they're not exactly parallel plates, they're slightly curved. But the student created this 3D CAD model of one gap between the two plates. And then they basically applied a uniform heat flux, so they added heat to both sides of this flow channel with water in it. And they looked at the natural circulation of the flow. Now, they also did this mesh convergence study. So they took their geometry and they used different numbers of cells to create their mesh and ran a simulation. And what they found was that for small meshes, less than about 20,000 cells, there were large changes in the exit temperature of the fluid from the system. So they found that in order to have a consistent and acceptable accuracy for their mesh, they had to have this range of more than 20,000 cells. Now, it doesn't make any sense to run a 70,000 cell simulation when you're going to get the same accuracy as a 20,000 cell simulation, because you need to optimize your computing resources and your accuracy, so you want to get the best balance. So you want to try to use a number of cells that's close to the low end of your acceptable range from your mesh convergence study. And then finally, the simulation was performed, and we were able to see that the temperature distribution between the two plates and the velocity distribution. So here the temperatures are in Kelvin. So 293 Kelvin is 0 degrees Celsius. So this gets up to 50 or 60 degrees Celsius as the flow exits from the gap between the two fuel plates. We also see that the velocities are small. Here we're only at about 4.3 centimeters per second velocity. So the velocities for this natural circulation flow in the MSTR are actually quite small.